Okay, folks, we are um, entering session or lesson number 8. Let me get to the present mode. And now we're entering into the physics of driving. And of course, along with physics means inertia. And that is all about restraining ourselves in our vehicle to prevent ourselves from getting injured in a collision. So let's get started with this. So there are some key terms. Most of these we know already from from school. So gravity, we know, is the force that pulls things down to the earth. Center of gravity is that point around which an object's weight is evenly distributed. So when we talk about center of gravity, we're talking about the car. Inertia is the amount of energy needed to propel a vehicle. Kinetic energy is an object in motion continues to move straight ahead until acted upon by some outside force. Traction is that outside force, right? The adhesion, friction, or grip between the tires and the road surface. And balance, vehicle suspension, the distribution of weight of the vehicle on the chassis of the car. So gravity does exist in driving, right? You can feel the pull of gravity as you drive up and down hills, for example. Driving uphill, you will lose speed unless you use extra power, right? Extra acceleration. Driving downhill, you will increase in speed unless you use the brakes, okay? You do not ride your brakes downhill. Don't do that, please. Instead, use engine compression by shifting into a lower gear. Now, I actually didn't write that comment, but I will say this. You should use your brakes to reduce your speed going down a hill. The only time when I recommend shifting into a lower gear is well ahead of the hill in a very snowy, slick environment to bring your car way down to speed and allow yourself to descend using your car's engine to keep you at a low speed. This is what trucks do on very sharp descents, right? You see those signs that say switch to a lower gear, use a lower gear. Okay. The only time when I would like to see our people doing this with an automatic vehicle is when they are still at the top of a hill and they want to bring, not only they brought their car already down to speed and they want to use the engine as an extra backup almost to the brakes when going down that slick hill. Okay. Gravity, center of gravity, the point around which an object's weight is evenly distributed. A vehicle's stability decreases as its center of gravity rises. Right? Okay. So stuff that has a high center of gravity is more likely to roll than, cars that have a low center of gravity. That's why sports cars all have a low center of gravity. That's why they're close to the ground. Okay. Natural laws in driving. Inertia. What is inertia? An object in motion continues to move straight ahead until acted upon by some outside force. Okay. I'm already thinking probably what you're thinking. I'm looking at that picture right here at the bottom and I'm thinking, okay, well, that car wants to continue going straight. This looks very much like my SUV. It looks like it wants to go straight around this corner. It wants to go straight off into oblivion here. It's just an extra force that's keeping it on the road right now, and that's called traction, right? Okay, these 5 factors can influence the effects of inertia. Speed, that's why we have this picture right here. Sharpness of the turn or curve, right? The size, weight, and height, and the load of the vehicle you are driving. The roadway surface conditions, right? These are not ideal roadway surface conditions for traction. The roadway slope. Recall how variables impact an accident. Can we take one of these variables away, one of these factors away from the accident? Okay, look at what we have here. If we reduce their speed, would that be able, let's say we have an accident. Let's say this car goes off the road and tumbles over the guardrail here. Okay, look at all the factors that we have into play here. Sharpness of the curve, the speed of the vehicle, the size, height, and weight of the vehicle, and the load inside. Okay, when we talk about load, we're talking perhaps passengers, for example, or maybe you have it loaded up with your stuff that you're moving to college. The roadway surface is one of those factors, right? The slope doesn't seem to, maybe there might be an uphill slope here. It doesn't look like there's a downhill slope. But in this accident, we always can control one of these factors. Which factor can we always control? Speed. Let's move along. How inertia impacts your car. Let's watch.
Newton's first law of inertia states that an object stays in motion, same speed and direction, unless acted on by an external force. Normally, a car and its occupants move around at the same speed. But when an external force is applied to the car, in this case by the crash test block, the occupants continue to move forward at the same speed until a force is applied to them. This resistance to a change in motion is called inertia, and it applies even when the velocity is zero. It's this property that enables people to do things like this. The china on the table stays pretty much at rest, even when the tablecloth's pulled from under it. That's because there's not enough sideways frictional force to overcome the china's inertia and get it to move. Back to the crash test. Because they're not wearing seatbelts, inertia means the occupants of this car continue travelling forwards until the windscreen applies the force to stop them.
Let's look at the inertia here. You can see the vehicle coming forward, it's stopping, but the occupants carry on because there's nothing stopping them carry on. That's the basic Newton's law here. So you can see the occupants, because they're unrestrained, the driver has hit the steering wheel and the whole steering column has crushed around him. You can see he's partially ejected and will be severely injured. The poor passenger, even though he was in the back of the car, protected by the front seat, because he's not restrained, he goes through the front seat and he's gone through the windshield, and you can see his head still sticking out there.
Of course, in real life, you get a lot less time to regret not doing up your seatbelt. Newton's first law gives us the idea that in a car crash, things keep going until something stops them. First used in the 1950s, seatbelts provide an external force that counteracts the passenger's inertia, bringing them to a halt in a more controlled way. But they're just one of the ways car designers reduce the forces on the occupants in the event of a crash. And every car designer also needs to understand the principle behind Newton's second law of motion.
Okay, so we can see that inertia wants to continue making us go forward, right? If we're in the car, we're in the vehicle, and we will continue traveling at that speed until some other force is acted upon us. And we could see there the force that was acted upon those two occupants. One was the windshield, the other one was the steering column. And in that case, and I don't think that car was traveling more than 40 miles per hour, maybe 45. In that case, we can be sure that those two occupants would have probably died from the force acted upon them to stop them. Okay, so seatbelts work as a way of, that is the most benign way of making that force, against inertia, that force that we need to stop ourselves, right? Otherwise, we slam into things that are going to hurt us, like the steering column or the dashboard or the windshield or even flying out of the car. All right. Kinetic energy in driving. Kinetic energy is the amount of energy needed to propel a vehicle. What happens when a vehicle's speed doubles? So, for example, your speed increases from 20 miles per hour to 40 miles per hour. Pretty common for us, right? You will need 4 times the distance to stop the vehicle as the speed increases. Not 2 times the distance, but 4 times the distance. Now, why is that? If a vehicle's speed doubles, the force involved in a collision will be quadrupled. The reason is because of kinetic energy and physics. Knowing this information, traffic engineers study traffic patterns and identify where driving errors might occur and determine safe speed limits for these areas. Okay, so we're going to get the stopping distance explained with some mathematics here. Kinetic energy, here we go.
Hi, Mrs. Phone here, and today we're going to look at stopping distance and reaction time, and kind of call this texting and driving, or the physics of paying attention when you're driving. Scenario, imagine you're traveling in a car at 68 miles an hour, and you look away for 1 second to change the radio station, check a text message, look at the pretty trees, see what the GPS is doing, charge your phone, plug it in. Why is it a bad idea to do this? The simple answer is obviously you can crash and die or kill someone, but we're going to break this down a little more scientifically and look at 3 separate variables that are involved with stopping a car. And the physics of the situation is we're going to look at the distance you actually travel in that second. We're going to look at the total overall human reaction and action time, and something called braking distance.
Okay, so these are the 3 variables here.
If you were to take 68 miles an hour and do some conversions or dimensional analysis, miles cancel, hours cancel, and so forth, minutes cancel, and we're left with feet per second. You were to do all the math. 68 miles an hour is 100 feet per second.
That's why he's using 68 miles per hour.
Or you do anything of that nature, your car is actually going to travel 100 feet during that duration. It's really important to kind of visualize how far that actually is. When I'm with my students at school, we actually go in the hallway and we measure that out.
Swoop.
Hi, Mrs. Sponer.
Sorry, guys. I'm sorry I did that. I wanted to stop it here for a minute to think about that. So,
68 miles an hour.
So if you're traveling at 68 miles per hour, you need to, how many seconds is this going to be? Something like 52 seconds it's going to take to stop. Maybe 5.2 seconds, 5.3 seconds it takes to actually stop your vehicle. Let's find out exactly what he means by that. So in that second, you travel one. Oh, okay, so this is the travel distance that you do in one second. So for every second, you're traveling 100 feet. So if you're looking away from your phone, or you're looking, let's say, we're not going to use our phone in the car anyway, but if you look away, let's say at your GPS or something else, maybe even off the road at some type of thing moving around, it's probably not going to be a whole second, but a half second is going to cost you 50 feet. I mean, you can imagine all types of potential hazards that can arise within 50 feet. It's all types of stuff. Let's continue.
Is 100 feet per second. So if you look away for 1 second or you do anything of that nature, your car is actually going to travel 100 feet during that duration. It's really important to kind of visualize how far it is. When I'm with my students at school, we actually go in the hallway and we measure that out. And it is a surprisingly large distance to realize that when you look away, that's how far you're going. In addition to that, we have something called human reaction time. And when you see a car in front of you slam on the brakes, you kind of look up and you have to recognize the danger. You have to realize what's going on. Your brain's a computer. It takes time to process that information.
And you got to decide what you want to do. Do I want to swerve off the road, slam on the brakes, close my eyes and cry? I don't know. And then on top of that, if you decide to push the brake pedal, your brain's going to send a signal down to your foot. You're going to take your foot off the gas and you're going to put it on the brake pedal. And you're going to slam it down, and then that fluid's going to go, probably hydraulic braking system, to essentially stop your car. All of this takes a little bit of time, and if you kind of think that all of this takes about a second, you're going to end up traveling about 100 more feet. And there is a way to measure human reaction time. If you were to take a ruler and have someone hold it, and essentially you were to put your hand right here, and when they drop it, you're supposed to clamp down. And if you look at this distance that it falls, since we know the acceleration of gravity, you can actually measure your reaction time. There's websites that do it too based upon clicking. And you would actually use this formula to do it, plugging in the variables. But I kind of put a chart up here. If you have a ruler at home, if you want to try this, you can actually measure your reaction time and get a quicker result than doing some math. And the last thing we want to look at is braking distance. It's important to note that the stopping distance of a vehicle is proportional to its kinetic energy. And kinetic energy is 1/2 mv squared. The stopping distance of any car is going to be dependent upon its velocity squared. And what that means is that's actually huge. If you're going 20 miles an hour and you double your speed to 40 miles an hour, what happens to your stopping distance? Well, your stopping distance is, your braking distance is denoted in red. At 20 miles an hour, it's 6 meters. At 40 miles an hour, it's not twice as much. It's not 12 meters. It's actually 24 meters. It's actually 4 times as great. It's a square. If your speed goes, if your velocity doubles, your braking distance goes up by 4 times as much. Likewise, if you were to triple your speed from 20 to 60, braking distance is 60, or braking distance is 6 meters. If it was just tripling, it would be 18 meters. But what does it do? It goes up to 55 meters. So you're traveling 3 times as fast. Your braking distance is 9 times as much. 9 times 6 is 54. Likewise, if you were to go from 20 to 80, and 80 is not even on a scale, what's going to happen to your braking distance? You're increasing your speed 4 times as much. So your braking distance is going to increase by 16 times, or 16 times 6, which is going to be a huge distance. So 6 times 10 is 60. It's going to be 96 meters. So that's going to be a very, very large result.
It's 102.
Up a lot. And I guess the gist is it takes nearly twice as far to stop at 70 miles an hour as it does to stop at 50. And if you kind of realize this, traveling at 35 miles an hour, your braking distance is like 45 feet. I mean, if you're traveling at 30 miles an hour and you slam on the brakes, it takes your car 45 feet before it comes to a complete stop. That's what braking distance is. Braking distances in themselves are a little nerve-wracking. If you're traveling 60 miles an hour, after you slam on the brakes, after you think about all this, and you have all this thinking time, after you slam on the brakes, your car is still going to go 55 more meters, and every meter is going to be a little over 3 feet. So you're looking at like 180 feet or so. And that's going to be a long distance, a very long stopping distance. The only saving grace here is if you're dealing with a car in front of you, and they slam on their brakes, they obviously have to undergo this distance as well. But if a child's running in the road, then that's not a saving grace anymore. So
Okay.
just some basic ideas.
I want to stop right there and just point out to you this basic fact, okay? This is physical fact. It takes nearly twice as far to stop your car if you're traveling at 70 miles per hour versus 50 miles per hour. Really, really think hard about that, guys. So that temptation to speed and to speed up and go from 50 to 70 miles per hour on the same stretch of road, it will take you nearly twice as much distance to stop your vehicle. Okay. And stopping our vehicle means we avoid collisions. Okay. We avoid accidents, we avoid injuries, and even in the worst case scenario, death. Okay. I want to let this man finish up with his tutorial here.
Before your vehicle will actually come to a stop. And that's
Okay.
a huge amount of distance.
This is very important too. Let me bring this back.
You're dealing with the car in front of you, and they slam on their brakes. They obviously have to undergo this distance as well. But if a child's running in the road, then that's not a saving grace anymore. So just some basic ideas. Braking distance at 68 miles an hour. It's about 250 feet. This assumes roads are dry, your tires are optimal shape, your brakes are good, and so on. So your stopping distance at 68 miles an hour comes out to be about 100 feet if you look away for a second. About another 100 feet for thinking, reacting, pushing the pedal. And braking distance is surprisingly about 250 feet. So you actually travel 450 feet around this area before your vehicle will actually come to a stop. And
That is a lot of distance, guys.
Not paying as much attention as you should, or driving a little tired, or possibly on some substance you should not be on. And if we were to just kind of break this down to city driving, at 35 miles an hour, if you looked away for a second to check a text or do whatever you're doing, you will actually travel 50 feet in that second. 50 feet while thinking and reacting, and your braking distance will be about 60 feet. Thinking about 160 total feet to stop.
Wow.
So braking distance alone is kind of nerve-wracking. Like if a child runs in your road and you slam on the brakes, your car's not going to stop on a dime. The faster you're going, the more your braking distance is going to increase. And it's not linear. It's proportional to the square of your velocity. So it's important to be conscious and drive safely and to maintain speed limits in residential areas and on the highway. But hopefully you see there's more going on to stopping than just slamming on your brakes and stopping your vehicle. There's reaction time, there's perception time, there's action time. Your brakes actually take time to stop your car, and you can go hundreds of feet in that process, regardless of whether you're on the highway or in the city. So hopefully this helps you. I know some of us are going to be getting our permits soon and driving. Hopefully you kind of use this to your benefit and drive safely. This is Mrs. Bone.
Okay, and we're going to stop here with our part one.